Hey everybody, Mr. Sewell here with a video that's going to take you through our slideshow on the known universe. And you'll find this on the week 3 page. So let's go ahead and get started as we begin our journey into the study of astronomy. Now, astronomy, you can read this. I'm not going to sit here and read everything for yourself, but just make sure you understand that astronomy is a study of everything outside the Earth. It's anything that is going to radiate or reflect any type of energy. And we call this electromagnetic, but electromagnetic energy takes in so many different types of light and heat, X-rays, gamma rays. Basically, pretty much any type of energy can be classified as electromagnetic energy. And so you can see this is a scale of electromagnetic energy. And right here is what we can see. This is what we call visible light. Everything over to the left and over to the right is outside of the human eyeball's ability to detect it. But it's still a type of energy. Infrared energy is another name for heat. And so you've got heat right here. Microwaves, radio waves. Radio waves are getting, these are really, really long wavelengths. This is 10 raised to the second power. And we're talking about wavelengths here. And if you get shorter wavelengths, you get into ultraviolet light, X-rays, and gamma rays. These are different types of energy signatures that you can see that are coming off of different galaxies. And so using different filters on telescopes, they're looking at different galaxies to take a look at their energy signatures and what kind of energy is coming off of them. And some artist has put together a image of what the universe may possibly look like based upon these energy signatures of different galaxies. Okay, so when it comes down to the universe, one of the things that we always want to know is how did the universe start? And the idea behind the beginning of the universe is something called the Big Bang. It is a theory that suggests that there was an expansion or an inflation of energy about 13.8 billion years, right at 14 billion years ago. And it took roughly about 300,000 years for this expansion to cool enough for there to be the first atoms. And if you know anything about matter, you know that matter is composed of atoms. And so this expansion took place for about 300,000 years before, and you don't have light or really measure any type of measurable energy until you have atomic particles. And so this is a neat theory to explain how the universe began. So looking at this theory from a pictorial standpoint, right here you have the Big Bang event. And then you have the first few seconds. After a few minutes and after about 300,000 years, you begin to get matter to show up. After a billion years, this matter is starting to coalesce into and form nebula and stars and galaxies. And then, of course, this is modern day. This is the modern day time scale. Okay, another poster. We always show this when we're looking at the Big Bang, but you can see the event takes place right here, and then there's a timeline, 10 to the negative 43 seconds. 10 to the negative 32. So these are just fractions of seconds, billions of billions of billions of seconds. 3 minutes into it, it says it's still too hot for atoms to form. 300,000 years, electrons are finally combining with protons, and you're getting the formation of hydrogen and helium, the two main elements of the universe. So it took quite a long time for the universe to cool down enough just to even have hydrogen and helium. Just some more facts about the theory. About 13.8 billion years ago, the universe began to expand. It wasn't an explosion as much as it was a expansion. So I'm going to pause the video at this point in time. You've got 3 videos to watch right here. They're not long videos. You got the origin of the universe. You got one on the Big Bang, and then another one here on the Big Bang as well. And these videos will help you understand all about the Big Bang. So take a few minutes and watch these videos, and then I'll pick up with my presentation here in just a minute. Okay, now you've had a chance to watch the videos. Let's move right along with our slide presentation. What we're looking at now is evidence for the Big Bang. And we've got three main points of evidence right here. Number one is called the red shift, or the red-shifted galaxies. And this is due to something called the Doppler effect. Now, the Doppler effect is when you have something that's moving either towards or away from a fixed object, the wavelengths of light coming off of it are going to be different. If it's moving towards you, the wavelengths kind of get bunched up in the front, and they're going to be shorter wavelengths. Shorter wavelengths in color are going to end up being more blue. And so if an object is moving towards the Earth, it's going to have a slight blue tint to it. If it's moving away from the Earth, then the wavelengths kind of get spread out, and longer wavelengths are going to be more red in color. And that's where the name red-shifted galaxies come from. When you look at, with these high-powered telescopes, when you look into the night sky and look at these other galaxies, they're going to have a certain color to them, and many of them are colored red, which means that they are moving away from our position. And so what it tells us is that the universe is expanding. Number two, 3/4 of the universe, or most of the universe, is composed of hydrogen and helium, which are the two most simplest elements. These are the elements 1 and 2 on the periodic table. They are very simple, and if you take hydrogen and helium, you can basically make up everything else just by combining these elements together. So we expect the universe to be composed mostly of these two elements, and that's exactly what we find. Thirdly, we see something called cosmic background microwave radiation. This is the radiation that would be emanating from an event such as the Big Bang, and we find it pretty continuous throughout the universe. We find it everywhere, and so what it is, it's the leftover radiation from the Big Bang event. And this is more on the Doppler effect. I'll let you look at these on your own, but you can see this in a moving car. As the car moves, the wavelengths get bunched up in front. If you listen to a car, you'll notice that it has a high-pitched tone, or a higher pitched tone as it's moving towards you. But as it goes past you, the tone will drop. And that's because the wavelengths are bunched up as it moves towards you, but as it passes you, the wavelengths get spread out. And so not only can we apply the Doppler effect to coloration changes in galaxies, it also can be applied to sound waves. And so you get, you all heard probably a motorcycle go past you, and you know that when it goes past you, the tone will drop. And it's due to something called the Doppler effect. And so the next couple slides are dealing with this as well. So here's some more videos. You get the redshift explained here, and then you've got the Doppler effect here. And so again, let's pause the video, give you a chance to watch these videos and get a better understanding of these concepts. All right, moving right along with our slideshow. Here's a chart. The next chart is on visible light. And again, this is talking about wavelengths, kind of showing you what happens at the blue end of the spectrum. And this is visible light. And so if you look, this is all the colors of the rainbow. And if we start on the long wavelength end and move down towards the blue, it goes red, orange, yellow, green, blue, indigo, and violet. And the acronym Roy G. Biv is used to remember those different colorations. This is continuing on with the Doppler effect. You've got the opposite of redshift, in which the wavelengths are getting spread out, giving a red coloration. You've got the blue shift, where something is moving towards a fixed object, and the wavelengths get bunched up, giving you a smaller wavelength and a blue coloration. Now, not all galaxies are moving away from us. There are some galaxies that are moving towards us, and the Andromeda galaxy is one of them. And it's estimated based upon the speed of this galaxy. You see it has a blue tint to it, which means it's moving towards our particular position. And it's estimated that our galaxies will collide in about 4 billion years. Luckily, we won't be around to see that take place. And so here's just another graphic that shows you, here's the Milky Way galaxy, which is our galaxy, and the Andromeda galaxy, and they're going to collide in about 4 billion years at this position. So, Hubble's law tells us that the universe is expanding and that galaxies are moving relatively away from each other from their particular positions at a proportional speed. And this is called the red shift. And so the greater the distance the galaxies are from each other, that means they've moved faster. And so they're going to be red shifted to a higher red coloration. And this is called Hubble's Law. And basically it's kind of like a loaf of bread that expands. When you put a loaf of bread in the oven, it's not very big. This particular type of bread is called raisin bread because it's got a bunch of raisins in it. And so they're all bunched up together. But once you put it in that oven, that bread begins to rise and expand, and you can see all the raisins move away from each other. Well, that's kind of the way that the universe works. Everything was at one particular point, and it began to expand outwards. And so you get all these galaxies that are moving away from each other or their relative positions, and then you get a red coloration. And so here's a good picture of the galaxies from one of these high-powered telescopes. And you can see all these different galaxies have these red colorations, which means that the universe is expanding. Now, a galaxy is a large group of stars held together by gravity. And when we say a large group of stars, we're talking on the neighborhood of 100 trillion stars. And so this is not just a small group, but this is massive amount of stars. Anywhere from 50 billion, it's estimated that there's somewhere between 1 billion and 1 trillion galaxies out there. So there's plenty of galaxies. Now, our galaxy is known as the Milky Way galaxy. And it's the shape of it is a spiral galaxy, and our sun is way out here on one of the arms. It's called the Orion arm. And so here's our sun, and then our solar system revolves around the sun. So we're nowhere near close to the center of our galaxy. And it's been estimated that if you were to travel in a spaceship at the speed of light from one side of the galaxy to the other, it would still take you 100,000 years to travel across our galaxy. That's how big our galaxy is. Another little graphic here to kind of give you an idea of the shape of our galaxy. So we've got several different types of galaxies. We've got spiral galaxies, which have bright centers with arms that spiral around them, kind of like the Milky Way galaxy. And then you've got what's called a barred spiral galaxies. And you have a huge number of stars in the middle with usually two arms that radiate outwards. You have elliptical galaxies, which are they don't have arms, but the whole galaxy is shaped like an ellipse. And then you've got irregular galaxies, which they really don't fit into any of the other categories. Their shape is irregular, but they are still held together by gravity. Okay, that is the slideshow on the known universe. Hope that this helps. If you have any questions, please let me know. Look forward to helping you out some more in class. See ya.